let's learn stack implementation in C using arrays and linked lists. So what is a stack? Stack is a linear data structure that follows a principle LIFO, last in first out. Both insertions and deletions are allowed only from the top. You can assume a stack to be a container which is closed at the one end, the bottom end, and operations can happen only from the top. And places where the stack is being used, in case of calls to user-defined functions as to where the control has to come back after the function body has been executed, or the default values that are stored in the function header, all these are stored in the stack memory. And then the undo redo operations, the last done operation is to be redone or to be undone. There again the concept of stack is used. Expression evaluation. So when we write a mathematical expression, it will be in the form of infix, where the operators are going to be fixed between operands. But when the system evaluates, it will convert it either to a postfix or a prefix notation. In case of a postfix, the operator will be fixed post to the operands based on the priority of operations. This again uses a concept of stacks. In case of syntax parsing, say for example I have an expression involving parenthesis to check if every opening parenthesis has a equivalent corresponding closing parenthesis. That matching of parentheses again is done using the concept of stacks. Now how can stacks be implemented using arrays? We will be using a static array, that is the size of the array should be known at compile time when you write the code, and we'll make use of a variable top which will track the topmost element in the stack. And the implementation using arrays is easy, but one limitation is it causes a stack overflow. A stack overflow is a situation where the stack becomes full and you cannot perform any more insertions. So to understand stacks visually, this is a linear structure that is shown with the top end open and the bottom end closed. So all operations like pushing into the stack or popping out of the stack can happen only from the top. So assume this is an array of size 5. The variable top is initially assigned to a value -1, and thereafter for every push we will increment the top, and in its place, that will refer to the subscript of the location where the element is going to be read. The next push operation, the top is first incremented, and to that subscript what top is referring to, we shall read the next value, and so on. So when top has reached the index of the last element, so for an array of size 5, when top reaches a 4, that will cause a overflow, which means after that we can't push further elements, we can only keep popping. Let's see how to implement this with a code. Let's have the global declarations first. So we'll have a variable stack that's going to represent my stack. I'll have it as an array of size 5. We'll have the size of the stack stored in a variable n, and then top to be initialized to a -1, and a variable val which is going to take the data to be pushed into the stack. Now let's go for the user defined functions. So we'll have the push function. Before I try and push a data, I have to check if the stack has provision to take more data, that is to check if my stack has reached a overflow situation. Overflow is when top has reached the maximum subscript. For a size array size 5, allowed subscripts are 0 to 4. So when top has reached a n-1, that will refer to a overflow situation. So I'll print a message, the stack is full or stack overflow situation, and then take the control from the definition back to the main. In case the stack is not full yet, I'll ask the user to enter the element that is to be pushed into the stack, and that element shall be read. The element that is read is going to be pushed into the stack using the expression stack of. We'll increment the top first, and in that subscript we shall have the element included as stack of plus plus top equals a val. So that will be the required statements for a push operation. Now after a push, I might want to show the status of the stack. So we'll have a user defined function display where the elements of the stack are going to be shown from the top to the bottom of the stack. So the stack status is going to be shown by running a loop starting from the subscript top till I reach the 0th subscript. I'll show the elements as stack of k. So this is going to show the stack status after a push operation. Let's do the user defined function for the pop operation. So just like we had a check for overflow, we must have had a check for underflow before I try to pop. So underflow is if the stack is empty. Now we could do that using another user defined function. Let's call it isEmpty. So this isEmpty function is just going to return a boolean value true or a false by returning the result of whether top is equal to a -1. So if top is truly a -1, then this is going to return a true, otherwise it will return a false. So making use of this function isEmpty in the pop, I'll have if isEmpty returns a true value, then I shall print the message the stack has got nothing to be popped, and I'll take the control from the called function back to the main. But in case there was something in my stack, I shall print the deleted element or the popped element as stack of k after the topmost stack of top, because the topmost element is what is going to be popped. After the topmost element has been removed, the subsequent element now becomes a topmost element, and that can be obtained by having a decrementation of top. So we are doing a post decrementation on top after showing the current element that top is pointing to. So these will be the required statements for a pop operation. And again, after a pop, I might want to call the display. So just like after every push, I'm trying to show the status of the stack by calling the display within. Same way, we could have a function call to the display after every pop, so that we try to show the status of the stack. Like we had the push and the pop operation, we could have an operation called the peek. So the peek is going to be a function where I'm just going to look at the topmost element. We're not going to update the top, we're just going to see the element the top is referring to. And like in case of the pop, we must have had a check if there's anything to peek in the stack. If there is nothing to peek, then we're going to show stack empty and take the control back. Or if there is anything in the stack at all, we can display the topmost element to be what the top is referring to. So using the placeholder, I'll display the element that is there in stack of top. So like I said, we're not going to update top, we're just going to display what the topmost element is. So with all the user defined functions done, we're going to perform this operations using a menu driven code. So I have a variable for reading the choice from the user, and the ideal loop for a menu driven code will be the do while. So I'll have the menu printed with these options shown in the menu, and I'll take the choice from the user as well. So this choice is going to be read using the variable ch that's been declared, and depending upon the choice, we shall call the appropriate functions. So in case the choice was a 1, we'll call the push function. Else, in case the choice was a 2, we'll call the pop function. Else, in case the choice was a 3, we'll call the peek function. In case the choice was a 4, we'll print we are exiting from the code before we break the loop. And in case the user enters any other number other than 1 to 4, then we are going to show the message it's an invalid choice option. So having completed the body of the loop, the terminating condition for the do while will be as long as the choice is not equal to a 4. So having included the statements, let's execute the code and see. So in case I had entered a pop or I had entered a peak before pushing, I'm getting the message stack empty. So when I choose to push, the element is red and the stack status is shown. I try to push again another element. So from the top, the element that is last pushed is from the top, the status is shown. So I have another element pushed, the status is shown. If I try to peek, the topmost element alone is displayed. A pop will remove the topmost element, showing the current status of the stack. So we can continue performing these operations of push and pop based on the user's choice. In case of stack implementation using linked list, we make use of a self-referential structure. We've already learned the user-defined data type structure. A self-referential structure is where, in addition to the members of the structure, we'll have a member which will be a pointer pointing to itself. So it references itself, and we make use of such a structure to create the nodes of a linked list. Linked list concept uses dynamic memory allocation, where memory is going to be allocated for every node at runtime. So every node will contain the data and a link. And the top node, again, will have a variable top which will point to the topmost node or the first node. There is no fixed size limitation like in case of an array. Understand linked list visually. Every time a node is created with the data element red and the next element, which is going to be a pointer, initialized to a null. Firstly, the top is going to be a null. So if the top is null, this node that is been created will now be the topmost element, like that. For the next push operation, again a child node is created somewhere in the memory, depending upon the availability of the heap memory. The data value is red and the pointer is made to point to the null. Since top is no longer null, it is pointing to one node already. The next of this child node that has been created will be made to point at the node that was already there, and the child node just now created will be made to be the topmost node. So like this, the list will keep growing. Let's see how to implement this with the code. Let's have the self-referential structure shown first. So I'll call this a stack. So like I said, we're going to have one member which is going to be the variable that will store the data. The other member will be a pointer of type structure. We'll call it next. So this pointer points to a memory location of type stack, of type itself. So this is a self-referential structure. And like before, we'll have some global variables. I'll have a s, originally initialized to a null. I'll have a top, initialized to a null. Within the push definition, we'll have the element to be red. Now we'll have to allocate memory dynamically. We'll have a variable of the same type stack. We'll call it node, which is going to be allocated memory from the heap. How much of memory will I want? I'll want a memory capable of storing this structure. And on allocating, supposing there was heap memory, this is going to return a pointer of type stack. So I can check if the node that was allocated memory is available or if the heap is full. So if there was no more heap memory, so this is where it's going to be an overflow condition. in which case I can say there is no more memory to be allocated and I can take the control out of the function. But in case there was memory, now the element that has been read here has to be assigned to the data member. How is that to be done? Node arrow val is going to take the value of the n that has been read, and the other member, which is a pointer, node arrow next, is to be assigned to a null. So these statements are involved in creation of a child node every time. After this, we'll have to perform the linking of these child nodes to form a stack. How is that going to be done? If my top is still a null, so first time when there is nothing in my linked list yet, top is going to be a null. So in which case the top will take the same data as the node is holding. So the node that has been created will now be the topmost node. Otherwise, so if there was something that my top is already pointing to, so as I showed through the illustration, the child node that was created, its next I shall link it to top, and I'll make this child node as the topmost element. So that's what I visually shown. The child node that was created is linked to the existing top of the stack, and this child node will now become the topmost node. So much for the push operations. So like before, we can show the status of the stack after every push and pop using a display. But before that, let's try and have the body of the display written. At any point of time, I'm not supposed to lose track of the topmost node. So I shall have of type stack a pointer called temp that is taking the same location, address location of what the top is pointing to, and I shall run a loop with that temp every time, showing with the appropriate placeholder the data what the temp is pointing to, and to go to the subsequent nodes, my new temp has to be changed to temps next. So when the this loop keeps happening, every node's data is going to be shown and temp is going to advance to the next nodes. At one point, the last node is what the temp will point to, and its next will be a null, at which point the loop will stop. So this will be required statements for the display UDF. Like before, isEmpty is going to be returning a boolean value depending upon whether top is pointing to a node or it continues to be a null. That isEmpty call is being done within the pop, and if there is an element in the stack which can be popped, the popped element can be displayed as top data, which will be top arrow val. Now on popping the topmost element after it's been removed, my top has to point to the next element. So my top will be updated to the current tops next. The highlighting difference between implementation of a stack through an array and through a linked list is, in case of an array, on popping, the element is not deleted. We are just manipulating the subscript top. We're traversing until the current value of top to give the user a feel of the element being deleted. But here, since we are dynamically allocating memory using the heap, as we pop the element, the memory used by that element has to be freed, has to be deallocated. So to get that effect, we'll have yet another pointer. We can have a temporary pointer which is taking the current value of what top is holding, and I'll safely advance my top to the next node. So the topmost node which is to be deleted is referred to by temp, and top has advanced to the next node. So it is now perfectly okay to free that topmost node that is identified by temp. So this is a main difference about linked list implementation. For every pop, the memory used by the node is truly being removed or deallocated. The menu options will be the same. So the main, there is no change. Let's execute the code. Before that, we must have had the standard library.h included for the malloc operation. Like before, if I had a pop or a peak chosen before pushing, I am getting the stack empty message. When I choose a push, the element is entered and the stack status is shown. Another push, the stack status is shown accordingly. A peak will show the topmost element and a pop will remove the topmost element, showing the current content of the stack to be just 100. If you had popped again, then the last element has been popped and the stack contains nothing. So this will be the way we implement stack using linked list. So when you try and make a comparison between the stack using array implementation and linked list implementation, in case of an array it will be a fixed size stack. For a linked list it will be a dynamic size. The access when its implementation is with an array is easy and faster, and there is an overflow condition in an array which is not there in a linked list. It only depends on the system memory, and how the memory is being used is different in case of a stack and the linked list. So here the memory allocation is done statically. In case of a linked list, memory is allocated dynamically using the heap memory. If you found this video useful, please do like, share and subscribe for more lessons on C. Happy coding!